anniversary meeting, and we have a special guest, as you probably know. So just a quick house keeping and some regular intro slides. So obviously we have Bryce today, C++ Horizons. Super excited to have him. If you would like to speak, have a talk here, anything works. There's tons of information I can help. It can be either something that you learned from your daily job, or you looked online and you want to share with the team, with the meetup. Anything from 5 minutes to 1 hour or more, everything goes. Talk to me, and we'll get it done. So feel free. That's a very good opportunity to learn something by explaining to others. So there's a lot of benefit from doing that. So yeah, contact me. This is sponsored by Qualcomm Wireless R&D, which I'm part of. Thank you. Thanks for my VP. Special thanks to Charles. Let me just open my camera also. At the end of the meetup, I'll share the slides, and obviously we have Discord that we can communicate. I am loading the recording to San Diego C++ Meetup YouTube channel, so you can browse the past events and enjoy the recording. We use our SDCPP Meetup handle on Twitter. I have my own handle on Kobe_CA. And CA is not California, just my initial of my last name. And no Mastodon for me right now. I didn't do anything related to this yet. I'm also uploading information about the recent meeting on Martin's blog post, and this is the link where I post everything. Okay, so welcome. By the way, welcome anyone that is new. Super happy to have you. Let's have the bio for Bryce. So Bryce has spent over a decade developing programming languages and software libraries. He is a principal architect at NVIDIA, where he leads programming language standardization efforts and drives the technical roadmap for NVIDIA HPC and quantum compilers and libraries. Bryce is passionate about C++ and is one of the leaders of the C++ community. He is the chair of INCITS PL22, which is the US Standards Committee for Programming Languages, and he also the chair of the Standard C++ Library Evolution Group. He also serves as the editor of the INCITS Inclusive Terminology Guidelines. Bryce served as the program chair of the C++ Now, which I think just happened, right? And CPPCon conferences for many years. On the C++ committee, he has personally worked on concurrency primitives, parallel algorithms, executors, and multidimensional arrays, which is awesome feature, by the way. He's one of the founding developers of HPX parallel runtime system. Welcome, Bryce. Great to have you here.
Well, thank you for that great introduction.
Sure.
Here, I'm gonna go ahead and share my slides with everybody. And
by the way, I missed no worries. I missed a few things in your bio. Your ADSP co-hosting, you are a PowerPoint wizard, and also a frequent flyer master. So these things I suggest you.
I did spend most of my day yesterday on phone calls with various airlines, and as my girlfriend will tell you, nothing makes me happier than calling into my airline's customer support desk. I don't know why. It's just I take a great joy in planning travel.
Okay, all yours.
All right, so let me just move the little Zoom thingy out of the way here. So as Kobe said, I'm Bryce Adelstein Lelbach. I guess I've done a lot of things in the C++ space. I've been working on programming languages and compilers for about a decade. And I chair the standard C++ library evolution group, which designs and standardizes the C++ standard library. And so today I'm here to talk to you about 3 features that the C++ committee is working on that I am quite excited about. So C++20 was the largest release in over a decade. It delivered 4 major features: modules, coroutines, concepts, and ranges, and dozens of other additions and improvements. C++20 is now widely available, with most implementations shipping most of C++20 in production. And we're increasingly seeing adoption and more projects and organizations switching to C++20 as their default. I know I think it seems a little odd for me to tell you this in 2023, but there is a long tail to adoption for new standards. So we are entering a phase now where C++20 is available in enough compilers and has been in the field long enough that we're really starting to see it in use. Now, the next C++ standard, C++23, shipped back in February. And there's a lot of exciting changes that are coming in C++23. To name a few, there's a bunch of enhancements and additions to ranges, completing a lot of the foundational work that we did in C++20. There's the addition of formatted output, MD-span, which is a multidimensional array abstraction, and the original reason that I joined the C++ committee in 2015. So I guess now I can retire. There's expected, which is a new error reporting paradigm, standard library modules, and deducing this. Now, in the months leading up to a new release of C++, our focus is often on what makes it into that release and what doesn't. And we tend to put longer term goals on the shelf. And today I want to dust off those longer term goals. I want to go take some of those things that we've sort of put on the back burner, and I want to look at them. I want to look at what's beyond C++20 and 23. What is next for C++ in the next 3 to 6 to 9 years? So I want to tell you about the 3 features that we are working on that I think are most exciting and that will revolutionize how we write C++ code. And those features are reflection, pattern matching, and senders. And our exploration today will focus on what we can do with these facilities, not the specifics of the committee proposals or the merits of different design decisions. This is a talk about possibilities, not details. Much of what I'm going to show you is tentative and in some places purely speculative on my behalf. In places where the design is uncertain, I have chosen the option that makes most sense to me, and I've just ignored the other ones. So this talk represents really my own views, and I don't think that any one individual can speak for the committee as a whole. Certainly not me. So take everything I say here with a grain of salt, I suppose, is one way of putting that. So first, let's talk about reflection. So reflection and metaprogramming go hand in hand. And what metaprogramming is really is the craft of creating or modifying programs as the product of other programs. Now, reflective metaprogramming is metaprogramming that incorporates data from the program that's being modified. So there's 3 key components to reflective metaprogramming. First, there's reflection. There's the extraction of information about the program from the program. Then there's compile time programming. We need some tools for manipulating that information. And then there's injection, which is inserting new program entities. And when we talk about reflection in C++ as a feature, oftentimes what we're really talking about is reflective metaprogramming, is the combination of these 3 things, the combination of extracting the information, manipulating it, and then importantly, injecting it back into the program. So I sometimes, as a shorthand, will like to call it reflection/injection. So let's take a look at a simple example of how we might use this. So this is a function that takes an enumerator and returns its name as a string. And here we're using a few different new C++ constructs, and I'm going to walk you through what they are and how they work. So first we have the reify operator, which takes a C++ entity, so a function, a struct, an enumerator, a variable, a namespace, and it produces a reflection. And a reflection is a handle to an internal compiler representation of the type T. So std meta info is the type for reflection objects. That is the type of thing that gets produced by this reify operator. Reflections can be manipulated and transformed just like any C++ object. So here we pass the reflection of the enum type T to the function meta members of. And meta members of returns a meta info that represents all of the enumerators of T. Now it returns it as a meta info object. And such a meta info object is a range. So we can use a range-based for loop to iterate through the elements. And the elements in this case are all of the members of this enumerator. Now we want to use this new compile time expanded for loop called template for. So the idea here is that you're iterating over a type list. So each element may be a different type, which a normal for loop would not allow. In each iteration of this compile time for loop, we want to check if the enum parameter of the function is equal to the value of the current enumerator. To do that, we need to take the reflection of the current enumerator and turn it back into a real entity. And we can do this with the splice operator. The splice operator takes a reflection value and turns it back into the entity that it represents. In this case, the enumerator in question. If the parameter is equal to the current enumerator, then we need to return its name. And we can get that name with another function that operates on reflections called meta name of. So here's another example. This one is hash append, a hash protocol that incrementally passes input to a hash algorithm. So this takes a hasher object and an object to hash. So first, we are going to reflect on the object that we're hashing. And we're going to use meta members of to get all of its members. Now, this members of function takes an optional parameter which filters for certain kind of members. In this case, we only want non-static data members. We don't want any function members. We don't want any static data members because those wouldn't be useful to include in the hash. So next, we do a template for over all of those data members. And we use the splice operator to access each data member. And we recursively call hash append on the member. All right, so here's a slightly more advanced example. So we can inject at class scope 2, which can allow us to build powerful wrapper classes. So this traced class wraps another type, adding a print call before invoking each of the underlying methods of that type. So traced has a data member of the wrapped object, and we're just going to call it payload. We use a template for at class scope to generate a member for each member function of the wrapped type. So this is again happening at class scope. So we're injecting things, new members into this traced class. So first we need to sort of reconstruct the signature of the underlying types method that we're working on. So first we're going to inject the protection, attributes, and return type of the member that we're wrapping. Now next, we need to name the method that we are injecting. We can't use the regular slice operator for this because it would inject the method of the underlying type. But what we want instead is to create a new method in traced that has the same name as that method in the underlying type. So think of the regular splice operator as injecting something akin to a pointer to member. We can only use it on an object of the underlying type, not on our wrapping type itself. So instead, we use the identifier splice, which operates at the lexical level and inserts a name. So now we need to generate the parameters for the method. And there's a lot of dots here, and it's a little scary, but I'm going to walk you through what's happening here. So here we're using what we call splicing pack expansion. So adding triple dots before a splice will cause it to expand to a parameter pack-like construct, which can then be unpacked with a trailing sequence of triple dots as shown here. So that's why we've got the triple dots that are appearing before those two splices are turning the thing into a parameter pack, and then the three triple dots at the end are doing the traditional parameter pack expansion of those parameter packs that we just synthesized. It's a lot of dots, I know. So then we are going to inject the qualifiers of the underlying method. And then finally, we move on to the body of the function. And we're going to generate the body. And in that body, we will print out the name of the method that we're calling. And we're going to use some of those meta functions, the name of functions, to get that those names as strings. And then next, we're going to generate the call to the underlying method on the underlying object that we've stored. And note that here we use the regular splice operator, not the identifier splice operator, because we're operating on an object of the type that we are reflecting on. So it's sort of like a pointer to member, like we're applying a pointer to member. Then we forward all the parameters, and then we inject the names of the parameters, again using the splice pack expansion. And here we use the identifier splice because we're referring to the generated parameters of the wrapping method, not the parameters of the underlying method. And with that, we're done. And so now when you create one of these traced objects, you pass it in an object of whatever type you want. And then that traced class will have a method for all the methods of your underlying object. And when you call that method, it will print out, calling, foo bar, and then it'll call foo bar. Reflection can also be a powerful tool for automating data layout transformations and optimizations. So one common optimization that can have huge performance impacts is switching between array of structs, where data is stored as a single sequence of multi-component elements, and structive arrays, where data is stored as one sequence for each separate component. Switching between the two usually requires structural code changes, as shown here. Now, array of structs is often more intuitive, but structive arrays usually offers better memory access patterns, which can be critical when parallelizing or vectorizing. So consider this code here, which implies an operation to just the red channel of a sequence of colors. So it will have a strided access pattern, and in some cases, it may have alignment issues which would inhibit vectorization. We can use reflection to write a wrapping type that automates transforming from array of structs to struct of arrays. So inside of this type, which we'll call SOA, and it'll be a template type, it'll take a single template parameter T. And then first thing we need to do is we need to get the non-static data members of the type that we're wrapping. And we do that just as we did in the hash append example. So then we're going to inject a vector data member for each of the underlying component types. So we're going to have in vectors where there's in data members of the original type T. This constructor here is going to initialize the wrapper from a range of the underlying struct. So from array of structs data. And we'll use a template for inside of this constructor to iterate over each one of these component vectors. And then for each component vector, we're going to resize it. And then we'll copy from the range of array of structs data. And we can make our wrapping struct of arrays type a range of tuples of references to the component. And so that way it can be iterated as if it was an array of structs type, even though it's actually a struct of arrays data layout. So for example, to write an indexing operator, we use the identifier pack splicing operator to get a pack to the element in each of the component vectors at the specified index. Then we use tie to return a tuple of references to those elements. The same approach can be used to create actual iterators and make this thing an actual range. But in the interest of brevity, we're not going to look at that in detail. I think this is enough to illustrate the general approach. So now we can take our natural and intuitive array of structs code, the thing that we originally wrote, and by simply changing the type of image from vector to SOA, the new thing that we've created, we've switched the code from array of structs to struct of arrays. And this changes the memory access pattern for our single channel operation from strided access to contiguous access, which is much more cache efficient and doesn't present alignment issues and can be easier to vectorize and parallelize. So I believe that reflection will fundamentally change how we write C++ code. Reflection will help us solve problems that today often require boilerplate, macros, or external code generation. Things like serialization, protocol and language bindings, instrumentation, logging, debugging, etc. It's going to change how we build and design libraries and how we evolve the language itself. So now let's move on to pattern matching. So C++ has two types of selection statements today. Switches operate on a single integral value, which is often too limited. You can't use them with strings, literals, or objects. Now, if statements, on the other hand, operate on arbitrary Boolean expressions. They're powerful and it can express almost anything, but they're often too complex and verbose. So we need something that's in between the two, a powerful but concise way to select and decompose objects. And that's what we get with inspect, which is a new selection statement for C++. It matches values against patterns and binds variables when matches are successful. Inspect is an expression, not a statement. So an inspect expression takes a parameter, the object to select against, and a series of patterns. There's a variety of different patterns available. I'll highlight a handful of them today. Each pattern is followed by a statement, which is taken if the pattern matches. Inspect stops at the first match, not at the best match. So constant patterns match if the object is equal to the constant. And then the wildcard pattern will match against anything. Constant patterns aren't limited to integrals or enums. They can be strings or any arbitrary object. Here's another example. This is Fibonacci written with inspect. So here we use the identifier pattern, which binds the value to a particular name. Pattern guards can be used to perform arbitrary tests for a match. Since C++17, we've been able to destructure tuple-like objects. And we can do that in inspect 2 with compound patterns. So alternative patterns can match different types in variant or any-like objects and in polymorphic objects. They can also be useful when working with dependent types in a template. Extractor patterns allow us to completely customize matching and decomposition by implementing our own extractor protocols. An extractor is an object that has either an extract or try-extract method. When an extractor pattern is used, this method is called with the value under inspection. And then if the result of that call has a value, it is matched against the child pattern. So for example, in the first pattern in this inspect, phone number.tryExtract will be called. And if it returns a value, that value will be matched against the compound pattern here. Now let's look at a slightly more advanced example that combines both reflection and pattern matching. So this is a very simple and probably quite buggy piece of code that will take some C++ object and save it as JSON. So our thing takes, some object T, and it's going to return to us a stood string. A more correct way of writing this would be to have it take, an iterator and write to the iterator, or to return a range or something. But we'll just use a stood string for simplicity. So first thing we're going to do, we're going to create, our string that we're going to return here. And then we're going to get all of the non-static data members of T, just as we did in some of our previous examples. Now, next, we're going to do a template for loop. This time, we're not going to iterate through all of the data members. Instead, we're going to iterate through the indices up to the however many data members we have. So we're going to do an index-based template for instead of an element-based template for. And the reason for that is so that we can handle the case that we are at the end. We want to make sure we don't put out a comma if we're the last data member. So then we're going to access whatever data member is at the index that we're at, and the stood meta info object, if the one that you have happens to be a range, it has an index operator, so it's random access, so that you can just do indexing like this and get whichever one that we're at. And so then first thing we're going to do is we're going to start a JSON entry for this member, and it's going to be a key value pair. And the key is going to be whatever the name of the member is. And so we'll use stood format to write that out to our string. And then we're going to have a big inspect here where we're going to inspect the member itself, and we're going to figure out what to do with that value. So if it's a bool, then we're just going to either write true or false. If it's a number, then we're just going to format it and write it out. If it's a pointer that happens to be null, so anything that satisfies the pointer concept, but that's equal to null pointer, then we will just write out null. If it's any other type of pointer, well, then we're just going to sort of give up here, and we're just going to write out the address of the pointer. And if it's a string, then we're just going to write out the string in quotes. And if it's a range, this is a little bit more of an interesting one. If it's a range, what we're going to do is we're going to take that range and we're going to apply this function that we're calling to that range. And then whatever the result of that transformation is, we're going to feed into format. And formats support for formatting ranges just happens to produce output by default that is compatible with the JSON output for arrays. So it'll have the square brackets and then a comma separated list of things inside of it, which is exactly what JSON expects. And then finally, if this member is any other type of thing, we're just going to assume it's some object, and we will call save JSON recursively on it, and we'll wrap it in some squiggly brackets. Unfortunately, because stood format uses the squiggly brackets to indicate placeholders, we have to do a little bit of escaping here, which is why there's a lot of squiggly brackets. And then finally, once we've printed out the value of this member, we need to close the key value pair that we opened up a little bit earlier when we first started working on this member. And then we want to check whether we are the last member. And if we're not the last member, then we're going to output a comma. And then that's it. And we will just return the object that we have created. And so that is a pretty simple and concise demo of how you might do something like serialization with reflection and pattern matching in future C++ revisions. So inspect gives us a powerful new way to select and decompose objects. It makes working with tuple-like and variant-like objects far more natural in C++. And I think it will revolutionize how we write our C++ code. It will make it a lot easier to express conditional logic and a lot simpler and a lot more natural too. All right, and finally, let's talk about asynchrony in C++. Today, C++ has no standard model for asynchrony and no standard way to express where things should execute. And that's why we're introducing senders, a model for asynchronous execution in C++. There are three key concepts in the senders model. Schedulers are lightweight, non-owning handles to execution contexts. Schedulers produce senders. Senders represent asynchronous work that will eventually send a signal. A signal is either success and a set of values produced by the work, failure and an error produced by the work, or cancellation. Senders can be composed together with sender algorithms to form task graphs. Receivers are connected to senders and process their asynchronous signals. Now let's look at a simple example. So first, we need to get a scheduler from somewhere. It could be a thread pool, it could be a tasking system, a GPU driver, etc. Then once we have a scheduler to start a chain of work on it, we call schedule, which returns a sender. That sender will complete on the execution context associated with the scheduler. Next, we use a sender algorithm then to compose work onto the sender that we got from the scheduler. This work will be performed on that same execution context. The sender algorithm will return a new sender, which we can use to add more work onto the chain. Finally, we wait until the chain of work has completed using sync wait, which will return the value sent by the final sender in the chain. The pipe syntax gives us a clean way to compose chains of senders in the order that they will be evaluated. Now, we at NVIDIA have developed a prototype of senders that supports CPU schedulers, GPU schedulers, and distributed schedulers. It's available open source on GitHub, github.com/NVIDIA/studexec. And one of the demos that we have in there is this simple electromagnetic wave simulation that solves Maxwell's equations on a uniform grid. And this is the entire solver loop, which is expressed as a graph of senders. Now, this code can be run with a variety of different schedulers. By changing just one line of code, the kind of scheduler passed to the solver, we can go from running inline on a single CPU thread to running in parallel on the CPU using OpenMP, to a single GPU, to multiple GPUs within a single node, to multiple nodes scaling up to thousands of GPUs. We've also ported a simulation from the Palabos fluid dynamics framework to senders. This simulation models carbon sequestration techniques. The porous structure that you see is sandstone saturated in salt water. The red bubbles are liquid CO2, which is injected at the bottom and travels through the sandstone because of buoyancy forces. Using a distributed GPU scheduler, we've run this application on up to 512 GPUs. With standard C++ senders, you can take this code and by just changing one line, you can scale from a single CPU thread to an entire cluster of GPUs. All right, let's look at another slightly more advanced example here. This is an asynchronous network read. The idea here is that we're going to first read over the wire a size of how much data is in the array that we're going to be receiving. And then after we've read that size, then we will allocate and read in that many bytes into some buffer. And so we're gonna have this simple little buffer class here, which will have a unique pointer to an array, an array unique pointer of bytes, and then a size data member. And so then we've got this async read array function here, and it is going to take some handle type, which represents whatever our underlying network protocol is. And it's going to return a sender that will send one of these dynamic buffer objects. And we'll start off our chain of senders by using this just primitive. And just is a sender factory that takes a value that is immediately available and turns it into a sender. And so in this case, we're just using it here to create a dynamic buffer to start our chain. And then we're going to use this let value construct here. And this let value sender adapter will allow us to create a scope that will keep the buffer alive for as long as we need it. So then inside of that let value, we have another just here. And this just is going to, we're essentially getting a pointer or a span to the size member of our buffer. And we're saying that this is a span that we want to be writable. And then we're going to use that as the buffer to a call to async read. And that call to async read will read up to size t bytes into that size data member. And then after that read is completed, then we need to go and allocate our buffer. And so we'll do that here. So the first thing that we'll do inside of this then is we're going to check to make sure that we read the number of bytes that we expected to read, which is the number of bytes that would be in this size member. And if we've read the correct number of bytes, then we need to go and allocate our buffer. And so we'll do that by just calling make unique with whatever size we're expecting to get next. And then we're going to return a span to that buffer that we just allocated. And then we'll do another async read, which should read into that buffer and fill it up. And then finally, we're going to have another then here, which is going to, again, check to make sure that we read the number of bytes that we expected. And then it's going to send that buffer, and then that will be returned from this function. And then whoever wants to consume that data can consume it by attaching additional sender adapters onto that sender. Okay, now we're going to look at another example, slightly more advanced one, a generic asynchronous and parallel inclusive scan. And we're going to write this as a pipeable sender adapter that will be something that we can compose with other sender algorithms. So it's going to take three parameters: a sender, which will expect to send the input as a range, an initial value, and the number of tiles to split the input into. So sort of the degree of parallelism that we're looking for. We're going to use the classic two-pass parallel scan approach, which requires temporary storage for partial results communicated between tiles. We need to allocate this temporary storage asynchronously once the prior sender has sent us the input. So we'll chain the then sender onto the prior sender. And in the body of the continuation, we'll create a vector to hold the partials results. And then we'll return both the input range and the vector. Next, we need to do the first parallel pass, the down sweep. And we're going to use the bulk sender adapter to do this, which is it's similar to the then sender adapter, but it creates n execution agents instead of just running your function on a single thread. It'll run it on n threads. So we'll use bulk to invoke the body of the pass for each of the tiles. So the first thing that we want to do for each tile is calculate the range of elements that belong to this tile. Then we take all of the elements in each tile and we perform a local serial inclusive scan on them, which we do right here. Next, we need to propagate information between the tiles. The sum of each tile needs to be added to the elements of all the preceding tiles. We've already computed that sum. It's the last element of the local inclusive scan. We store that result into the partials vector. Assignments to partials from different tiles may happen concurrently, but that's fine. Each tile uses a different and unique slot in partials, and no one reads from partials yet, so there's no data race here. Then, after all the tiles have completed their local inclusive scans and written to partials, we need to have one execution agent do a serial inclusive scan of partials. We do this by piping another then sender onto the chain, which will perform the partials inclusive scan. This then sender will again pass along the input sequence and the partials vector. The result of the scan over partials looks like this. The information that each tile needs to add to its elements is in the partial slot for the tile directly preceding it. Now we need to go parallel again to distribute the information within all tiles. This is called the upsweep pass. So we'll pipe another bulk once again over all of the tiles. In the body of this bulk, we'll need to calculate which elements belong to the current tile, just as we did in the downsweep pass. And then we use a serial for each to increment each element in the tile by the appropriate value from the partials vector. After that addition, we will have the correct result in each element. Finally, we want the sender returned by our asynchronous inclusive scan to only send the input sequence, not the partials vector, which is a temporary that we no longer need. So we add a final then sender, which only passes along the input. The partials vector will be destroyed when this then sender completes. And that's it, we're done. We have a generic asynchronous and parallel inclusive scan that we can run on any scheduler that we want. All right, so reflection, pattern matching, and senders. I believe that these are the three most exciting C++ features that we're working on. Combined, I think they'll radically improve how we express ourselves in C++ and allow us to elegantly solve problems that are challenging today. All right, anybody got questions?
I'll start if that's okay.
Go for
Thank
it.
you. Thank you for the. It's a great overview. This is very exciting. Question. So I'm not very familiar with the meta class that Herbs proposed before. Is the reflection somehow related to this, or it's completely two different paths?
I don't think there's a lot of appetite in the committee for that.
Okay.
I'm focusing on things that are sort of actively being worked on, and the meta thing, it was presented one time. It did not have a particularly warm reception, and then I haven't heard of it at all since. So like these three things are all things that that like the committee's actively working on, that have been reviewed multiple times, that I think are mature. It's difficult for me to speculate about various other proposals, but that one in particular, I don't expect to really go anywhere, just because we haven't heard any updates on it in a while. I'm going to try closing my laptop so I can move my webcam down, and hopefully it will stay connected. There, can everybody see me now? That's a little bit better.
Yeah. Okay.
All right, other questions? Yeah, I see a David Holmes.
So how likely are we to see this in C++ 26 or 29 for any of these?
Well, that's a good question. For senders, it's been design approved for C++ 26. So it's been forwarded out of the library evolution group. So I'd give that one north of 80% chances. I think other people would probably give it higher odds than that. It's sort of past the difficult stage. So I think that one's pretty likely. For pattern matching, there's there was a lot of active work on it before the pandemic. There's not been quite so much work since then, or not as much active work. But the past year or so, there's been a good bit of progress on it. Some new ideas have come around, and I think that the major champions of that work, I believe, are still actively pursuing it. And I think we'll see some big updates in the next year or so. However, it may already be too late for C++ 26. It's a very major language feature, and we really needed to make a lot of progress on it and mature it during the past 2 to 3 years. And I don't think we've done that as much as we have for other proposals. Reflection is sort of in the same place. The difference with reflection is that we had a TS design for reflection that we shipped, but then we decided that we want to go in a different direction for what we're going to ship in the C++ standard. Essentially, we tried one thing out in the beta, and based on some of the feedback from the beta and some things that we've learned since then, we decided that we want to go in a different direction for the general release. Now, the problem is that some of the core contributors there are no longer working on it. Some of the other core contributors don't necessarily have the bandwidth. So it has been to some degree stalled. Now, I've got some indications that we may make some progress on it in the next few meetings. I've been asked for us to review it at some point during the C++ committee meeting in Varna that's in a couple of weeks in Library Evolution. But overall, I'd say pattern matching is maybe like 50-50, whether it's going to make it into C++ 26. Reflection is maybe like 40% chance of making it. Senders is the only one that I feel like fairly confident about. And I realize that's a pretty grim outlook, but just remember that's not my fault. My responsibility is starting in with the standard library, and we've been shipping our stuff. So, all right, any other questions?
Sender and receiver. So I remember being in CPPCon, the last one, attending one of the talks about sender and receivers, and there was like after the talk there was a huge debate or kind of discussion about, do we have a way in the abstraction of and the API to control where we actually run the jobs? Like think about affinity. Is
Yeah,
this
that's the whole point of the thing. Yeah. So I would say
okay.
yes.
Okay.
That's the whole purpose, is to control where things run and to be able to control where every specific thing runs. And a great deal of simplicity has been sacrificed in the interest of that cause. So yes, that is its primary redeeming function.
That's great. See someone raising hand.
Thank you so much, Bryce, for your talk. So I have a question just to follow up what you just mentioned. Since some of the committee members are working on some of the features, so I was wondering if you can describe like how like that process looked like. Apparently, the compiler commercially doesn't support a new language feature yet. So how do you like test it, a new feature, and things like that? Thanks.
Well, I mean, the reality is that we write the spec for the thing, and then we vote the spec for the thing into the standard, and maybe, like in an ideal world, we have an implementation before we've shipped it, and we do a much better job of that than we used to. But the reality is we do some prototyping, we write the spec, and then we put the spec into the standard. And then as we get closer to shipping that standard, the vendors do their own prototyping, and then we get feedback from them, and then we fix all the problems. The compiler vendors, for the most part, do not have the bandwidth to make significant investments into feature innovation before things ship. There are a lot of the major proposals are driven by people who work at compiler vendors or who work on compilers, but it's a lot of work doing the day-to-day maintenance on a compiler, and a compiler vendor is very rarely going to say, "Oh yeah, let's build out a prototype of this thing, and then we'll ship an experimental version." Before it's even like really solidified on the committee. So, somebody on the committee, I know a lot of it is like design work before prototyping, and then somebody on the committee goes and does a reference implementation, usually on one of the major open source compilers, and then people play around with it. And then sometimes that reference implementation turns into the implementation that gets shipped. Sometimes for, simpler features, the reference implementation is really just like somebody went and hacked it together in a weekend. So really the main, we do a lot of vetting on the committee when we write the proposal and write the specification, but a large part of our vetting process is that we have a release cycle that takes about a year once we're finalizing the standard, and it gives us a chance to collect feedback and identify bugs and fix problems. It's not the best process, I would say. Like if I had to rate it as a process, I would give it pretty low scores. There are better ways to do this, but it has been slower to change and modernize the process than I would like.
Thank you.
Cool.
Anybody got anything else?
I think it's a wrap. Thanks, Bryce.
All right, cool.
It's great. Thank you.
Well, next time I'll come visit y'all in person. I'm sure I'll be out in San Diego at some point.
Sounds awesome. Let's do that.
Yep.
Thanks, Bryce. Thanks, everyone.
All right. Great talking
Enjoy
to
your
y'all.
night. Take care. Thanks.
Thank you. Bye.
Thank you.
Bye-bye.
Great.